So we are team 5, and this presentation is presented by me, Balrasa Haran and Mariano Rubio. The title of our presentation is Estimating the Geothermal Potential of Heat Exchanger Anchor on Curtain Cover Tunnel. And this is our presentation layout. And the motivation for this paper was to find out the alternative solution for the energy requirements for heating and cooling of the building. Thermal analysis were performed on soil surrounding anchors with fluctuating heat inputs and also with differing water tables using diagram for FA code, and that is based on conservation laws. Based on yearly heat input to the soil and water table levels, the result shows that anchor's maximum heat rate is 4 watt per meter. And if we multiply the produced heat per year and per meter of anchor by the total length of the anchor within 1 kilometer of tunnel, such that approximately 54 kilometer of anchor per kilometer of tunnel, it provides capacities between zero point 0.4 to 0.8 gigawatt hour per year. And this is a general schematic of the tunnel. Here we have tunnel of 7 meter by 10 meter. This is diaphragm. These are anchors, and this is covered by the soil. And this is direction of heat. And, as per this graph, this is blue one is exterior temperature and red is interior. So heat will flow from higher temperature to lower. So for initial, the heat will go out, and then the exterior temperature higher than interior. Then heat will stored in the ground, and then all after September, it will go out. So this is our numerical setup. For the original analysis used boundary condition on border to mimic varying temperature and water table conditions. And we used the same boundary conditions, and we used ANSYS Fluent for our analysis. So mesh didn't align. We have here mesh size of 3,716 nodes for defining 3,493 elements, and here they have mesh size of 4,988 nodes defining 1,722 elements. And for the right wall, they have boundary conditions of like they have pressure imposed and it's adiabatic. For top one, it's impervious and temperature varying with time. For left, it's impervious and adiabatic, and for bottom one, it's impervious and fixed temperature at 284 Kelvin. We are only taking symmetrical half of the tunnel. And now Mariano will continue.
So just like Balraj said, what we did was we went ahead and created the mesh on ANSYS mesh and treated the boundary conditions, specifying which side was adiabatic and what side the temperature was inputting through. We also specified a water pressure to mimic the water table or simulate the water table level on one side of the soil. So, we went ahead and once we set up the boundary conditions, we ran through about 10,000 iterations to actually see what the heat extraction was at the anchors themselves. One thing to note was that our model actually did not have a collection zone like what the original analysis had. And though we got very close in our results, we feel that that may have been one of the things that impeded reaching the levels that the original heat flux extraction was for the original paper. When we initially set up the boundary conditions, and specifically the internal mesh, we were specifying two conditions, or analyzing two different conditions, one being a slightly permeable soil and the other being a non-permeable soil. And we were essentially using the properties given in the original analysis concerning the soil grains themselves, the air within the soil, and the water within the soil. And of course, that was due to the porosity of the soil itself. And by treating them as three separate items, we noticed that the original analysis wasn't, or when we redid the analysis, it wasn't originally giving us the results that we were expecting. In fact, we're getting about half of the values, or half the size of the values that the original analysis had. So we went back, and instead of treating the constituents of the soil as three separate items, what we did was we went ahead and used the equations to calculate the density, the specific heat, the thermal conductivity of what we call the saturated soil, basically the water, air, and grain constituents as one unit, and just doing the calculations to treat it as one mass for our internal mesh. And so doing that actually gave us much closer results to what the original analysis was. And so we basically inputted temperatures on the top boundary condition, mimicking soil temperatures throughout the year. And we could see that on the months that have higher temperatures, we saw a greater heat extraction. Months that had colder temperatures, we saw the heat actually get injected back into the soil from the anchors themselves, and it was very close to what the original analysis showed. In fact, we had about only 3.87 watts per meter versus the 4 watts that the original analysis showed. So that's about a 3.25% error. And also we were using the same optimization multiplier that was used in the original analysis. And so we could see the calculated heat flux labeled CE. And then using the optimization factor, we could see that the CEI represented what the optimized heat flux would be. We also did that for the non-permeable soil. Though we didn't quite get as high as we expected, we did get much closer than our first try. So we're only at about 10% error in this case. And we can see we got a fairly consistent result to what the original results had. So ultimately, the reconstruction results were still slightly below what the original paper had. And we feel that there were slight variations in the modeling anchor sizing and the collection zone that was missing from our design that may have contributed to slightly lower numbers. The mesh, the grid wasn't exactly the same, didn't line up as linear as the original one. So there were slight discrepancies there. And we also noticed that there was a slight marginal effect due to the water table. Ultimately, by calculating the properties of the saturated soil as one complete material instead of individual materials, we did get closer to the original results. And then by applying the temperature to the top boundary and varying temperatures, we did see a month-to-month variation very close to the heat flux variation going into and out of the anchors themselves. Here's our references, and thank you.